Good day to everyone who are joining me today. I am Mark Stephen M. Talag, and I'll be your presenter for this research. Wherein, in this presentation, I will be discussing the research by Polina Lemenkova, entitled Seismic Moment Tensor Solutions for Geophysical Mapping of the Philippine Sea Basin by GMT. This is a study that focuses on how seismic data can be effectively mapped using GMT or generic mapping tools, which is a powerful scripting tool to better understand the seismic activities in one of the most tectonically active regions of the world. And to set the stage, let's begin with some background information. The Philippine Sea Basin is located in the western Pacific Ocean, known for its high seismicity due to subduction zones along its margins. These seismic activities are not just important for understanding the geological processes of the region, but also for managing natural hazards like earthquakes and tsunamis. However, mapping seismic data in such a complex tectonic environment presents a significant challenge. Traditional methods of seismic mapping, which often rely on graphical user interfaces or GUIs, are not well suited to handle the large volumes of seismic data efficiently. This limitation is where GMT comes in. GMT provides an automated scripting-based solution to map seismic data with high accuracy, making it ideal for studies in seismically active regions like the Philippine Sea Basin. And now that we understand the broader context, let's dive into the seismic activity in the Philippine Sea Basin. This region experiences frequent seismic events, primarily due to interactions of three major tectonic plates: the Pacific, the Philippine Sea, and the Eurasian plates. Subduction along these plate boundaries generates significant seismicity, including submarine earthquakes that occur in the upper mantle. The research focuses on visualizing this seismic data to better understand the underlying tectonic processes, and by using GMT, the study aims to provide a clearer, more accurate visualization of these seismic events, helping researchers and decision makers better prepare for potential natural hazards. And given the complexity of seismic data in regions such as the Philippine Sea Basin, traditional GIS tools often struggle to provide the necessary detail and accuracy. The sheer volume of data, combined with the intricate tectonic features, makes it difficult to visualize and analyze the data effectively. This issue is further compounded by the lack of detailed seabed topography in the Philippine Sea Basin, which hampers geological exploration and resource management. The research addresses this gap by proposing the use of GMT, a scripting-based cartographic tool, to automate the mapping process and allow for quicker and more accurate visualizations of seismic activities. And with this problem in mind, the study set out three key objectives. First is to automate the seismic mapping using GMT to improve efficiency and accuracy. Second is to analyze seismic moment tensors to better understand the forces driving seismic events in the Philippine Sea Basin. And third is to optimize geophysical workflows to enable more efficient and reproducible mapping of seismic data. And by meeting these objectives, the study aims to enhance the understanding of the seismic activities in the Philippine Sea Basin, and also demonstrate the effectiveness of using GMT for geophysical mapping. Now let's take a moment to explore GMT, the tool that underpins this study. GMT is a powerful open source tool designed to automate map creation through scripting. And unlike traditional GIS software that relies heavily on graphical interface, GMT uses command line scripts to generate maps, which makes it highly efficient for processing large and complex datasets. And in the context of geophysical mapping, GMT excels because of its modular design and flexibility. The tool's ability to automate repetitive tasks means it can generate maps with minimal human intervention, increasing both speed and accuracy. And in this study, GMT was used to map seismic data, including earthquake locations, magnitudes, and depths, with high precision and reproducibility. Now, moving on to the methodology. The study utilized several key data sources, including GEBCO, CMT catalog, and ISC seismic data. These datasets provide the foundational seismic information required for the study, and using GMT scripting modules, the data were processed and visualized. For example, the PS Mecha module was used to visualize the focal mechanism of earthquakes, while PS Velo helped map the velocity ellipses in the region. The scripts were designed to automate these processes, making it easier to handle the large volume of seismic data and ensuring that the results were both accurate and reproducible. Now let's take a look at the results. One of the key findings of the study was the mapping of seismic moment tensors, which are crucial for understanding earthquake mechanisms. Moment tensors represent the forces at play during an earthquake and are essential for interpreting the tectonic processes that lead to seismic events. And using GMT, the study visualized these moment tensors in the form of beach ball biot diagrams. These diagrams display the focal mechanisms of earthquakes, showing areas of compression and dilatation. And by examining the seismic data from 1976 to 2010, the study identified key patterns in seismic activity, including the prevalence of shallow focused earthquakes along the subduction zones of the Philippine Sea Basin. And another important aspect of the study was velocity mapping, which was done using GMT's PS Velo module. Velocity mapping provides insights into the movement of tectonic plates by visualizing velocity ellipses and rotational wedges. These visualizations help geophysicists understand the dynamics of plate interactions and how seismic forces are distributed across the region. The velocity maps reveal significant tectonic motion along the subduction zones, showing how the Pacific Plate moves in relation to the Philippine Sea Plate. These results help improve our understanding of the forces driving seismic activity in the region and contribute to our knowledge of plate tectonics in the Pacific Ocean. And to summarize the study successfully demonstrated the effectiveness of using GMT for geophysical mapping in the Philippine Sea Basin. And by automating the mapping of seismic data, the research was able to produce accurate, reproducible maps that provide valuable insights into the region's seismic data. GMT proved to be a powerful tool for visualizing complex geophysical data, offering a significant improvement over traditional GIS methods. This approach not only enhances our understanding of seismic activity in the Philippine Sea Basin, but also has a broader implications for seismic hazard assessment and disaster preparedness in other tectonically active regions. And based on the findings of this study, I recommend the following steps. First is to expand GMT's use. GMT's capabilities should be explored in other seismically active regions to improve seismic hazard mapping and risk assessment. Second is to integrate real-time monitoring. Incorporating GMT with real-time seismic data would allow for a more dynamic and timely mapping of seismic events. And third is the training programs. To maximize the utility of GMT, I suggest creating programs for geophysicists and geologists to help them integrate GMT scripting into their workflows. And by adopting these recommendations, we can further enhance the precision and speed of seismic data visualization, which is both crucial for understanding and mitigating the impacts of seismic hazards. Thank you for your attention. This concludes the presentation on the Seismic Moment Tensor Solutions for geophysical mapping of the Philippine Sea Basin. And if you have any more questions, I'd be happy to discuss them further. Thank you.